All right. Hi, guys. Can I get a sound check?
Yeah, we can hear you.
We can
Yeah.
hear you.
We
Great.
can hear.
Thanks. Let's see. Let me get this. What is going on? Start. I'm just getting going here, guys. Sorry. Screen. Okay, cool. So let's see. I think the main thing we covered last lecture, just a quick overview, is some of the key concepts of having the CMOS static logic. And the main idea I think we covered was that you would have a pull-up network and a pull-down network. The pull-up network is made from PMOS transistors, and the pull-down network is made from NMOS transistors. Where the NMOS and the PMOS connect together is the output. And then the inputs go to both the pull-up and the pull-down network. And that the pull-up network and the pull-down network are never on at the same time. So in CMOS logic, you don't have static current flow. So you don't get a short between the power supply and ground. So in a static way, in transient sense, you do. And so that's a huge advantage for CMOS technology because it means the power consumption is fairly low, is on the low side. Let's see, what else did we cover? And then we talked about how we would create these compound gates. We would basically first use the equation, the non-inverted equation, to draw the N MOSFETs. Then we would take the complement of that and draw the P MOSFETs, put those on top. The output is where they meet, and the inputs goes to both. Did you guys? I know there was a question about. I think we were talking about what you do if you wanted to make the non-inverted version. And I think there was a question about why. It wasn't really a question, it was sort of a statement. I forgot who made it, about using P MOSFETs on the pull downs. And we'll get around to that, I think, in a bit. But anyway, so that for the time being, basically, I would say that either you would have to invert what happened? You'd have to either invert the inputs or invert the output, short of putting P MOSFETs on the pull down, which I'm gonna claim for the time being that it's gonna have its own problems. Okay. Any questions up to this point? So this would be something that's pretty handy to know, is like how to go from an equation to a circuit. Okay. Any questions? So if not, I think we can talk about sort of the next level of this simple model of NMOS and PMOS. So far in the slides, we said, an NMOS, we just had a really simple thing that it'll be if, let's say, what do we call this guy? In. If in is equal to 1, it's a shorted switch. And if in is equal to 0, it's an open switch. Okay, and the PMOS, if in is equal to 1, it's an open switch. And if in is equal to 0, it's a closed switch. Okay, so far, it's just like a perfect switch. So the next thing we're going to say is that it actually depends on, it's not just a switch, but it also depends on what's on the source and the drain nodes as well. So what we're going to say is that, and then these are all models, simplified models of how the transistor really works. But basically we're going to say an NMOS, if in is equal to 1, yes, it is a switch, okay? But it's a switch that if the input, so this is the source, if the source is at a 0, it'll really do a good job of getting that 0 in there. Okay, so 0, it transmits really nicely. Okay, but a 1, if it's trying to pass a 1, so this is logic 1. If n is equal to 1, and if it's trying to pass a logic 1, so logic 1, I'm just going to violate the terms of calling something logic. It's going to pass that, but it's kind of like pass it not so well. Let's say you get a logic 0.8. We all know there is no such thing as logic 0.8, but you're just trying to indicate that it doesn't do so good passing a high voltage or an equivalent 1 value from source to drain. So this is part of the reason why you always connect the pull down network is all N MOSFETs, because all they're doing is they're passing a 0 to the output. So they're either passing a 0 to the output or they're in a high impedance node, because they're not good, and MOSFETs are not good at passing ones. Okay, so P MOSFETs are the opposite. P MOSFETs, let's say the input is 0, means that it's on. It's really good at passing a 1. So if it's like this, you get a switch, 1 goes to a 1. But it's not so good at passing a 0. So again, if the gate is 0 and you're trying to pass a 0, you'll get kind of, if you're trying to pass a logic 0, you'll get a logic, I'm just going to call it logic 0.2. So not so hot at passing 0. So that, again, that's why the pull up is P MOSFETs, because all you're doing then is passing a 1 or you're off. So you're helping your elements, which are these transistors, to act kind of in their ideal situations. Okay, so so if for example you had, again, I'm just claiming this, not showing to you how this works, but if you had P MOSFETs on, if your pull down network was made out of P MOSFETs and your pull up network was made out of N MOSFETs, if you did something like this and you looked at the output, your output wouldn't quite swing from 0 to 1, from logic 0 to 1. It would sort of, you'd lose some of your headroom, meaning that you would have a noisier signal because you're not using that full available noise margin or signal to noise value. And then the next logic gate that you're driving is also, you're driving it with a weaker signal, and you'd sort of propagate that weakness through your system. So anyway, we're adding this concept that not only N MOSFETs and P MOSFETs are switches, but they're switches that have a preference as to what kind of signal they're passing. Do you guys have a question about that? And again, don't worry, we're going to get into the details of how NMOS and PMOS work. I mean, to a certain extent, and you'll come back and see how this relates to this concept. But right now, we're like trying to play with like simplified models, and we're saying that it's not such a strong switch when NMOS tries to pass a 1 or PMOS try to pass a 0. Any questions about that?
Oh,
okay. So, so sometimes, okay, so that's why you have N MOSFETs on the pull down and P MOSFETs on the pull up. But just like anybody else, CMOS circuit designers get lazy, and it's easy. Sometimes it's easier to do something other than just pull down and pull up networks. Sometimes this takes too much, like too many transistors, and we'll see like what type of circuits that's the case for. And people actually try to use a um, um, what we call pass transistors. That means you're trying to pass a 1 or a 0. Let's, for the sake of discussion, right? Let's say you wanted to, well, no, let's not get into that. But sometimes you want to use a pass transistor anyway. So this is just, I think this is just saying what I just drew. So I'm going to pass through here. Okay, so because, well, let me jump ahead and say, let's say you're trying to put, let me just jump ahead to say why you need to use a pass transistor. Let's say you want to build a multiplexer, okay? So a multiplexer is a circuit where if you have, let's say, a 2-input multiplexer, you have 2 inputs, D0 and D1, and you'd like one of them or the other to go to the output depending on uh, the status of the select. So S is select. So if S is 0, okay, if S is 0, the output Y follows the input D0 and it just ignores D1. So in the case that S is equal to 0, if D0 is equal to 0, then Y is equal to 0. And if D0 is equal to 1, then Y is 1. And the circuit doesn't care what D1 is doing. And then in the case when you select select 1, meaning you're selecting D1 to go through, you just follow D1. So the output just follows D1. And it ignores D0. Okay, so that's just a multiplexer. Hopefully you guys have seen it before in your logic classes and stuff. Okay, so let's look at a case where you have, what am I trying to show here? Let's see. So let's say you want to create a multiplexer out of gates. Okay, so the question is, how many transistors do we need if we want to make it out of gates? Okay, let's see if this will do. Okay, hey, it worked. So this is what you end up with if you were just going to make it out of gates, right? You would end up with 2 NAND gates, because this is the equation for the multiplexer, is you basically, this should be, sorry guys, the equation isn't showing up well, and because I had to put it in, anyway, sorry, won't tell you about my technical difficulties, but the equation should be Y is equal to S and D1, or S bar and D0, okay, which is implemented by this top circuit here. And because, I claimed that CMOS gates prefer inverted versions, so it's hard, for example, to make an AND in CMOS. It's a lot easier to make a NAND. It's hard to make a NOR. It's a lot easier, it's hard to make an OR. It's a lot easier to make a NOR, and so on and so forth. So to actually implement it with CMOS gates, it ends up being this complicated circuit, okay? So you end up with, let's see, 2 NAND gates, 4 inverters, and 1 NOR gate, okay? And then these numbers in these gates represent how many transistors each gate has. So I think we already saw that a NAND has 4 transistors, and NOR has 4 transistors, and inverters each have 2 transistors. Okay, so let me just have to take it out of, okay, great. So that's 20 transistors. Come, I can't take this thing out of, sorry guys. Hello. Okay, thank God. All right. Okay, so going back, so we had 20 transistors, and we had a bunch of NANDs. NANDs sort of look like, no, sort of, sorry. NANDs look like this. It's really good to know these like the back of your hand, like NANDs and NORs and those kind of things. So anyway, in NAND, the pull-up network is 2 parallel Ps. So if this is A, B, and Y, so A, B, B. Okay, so a NAND, 4 transistors, 2 P MOSFETs, 2 N MOSFETs, and the N MOSFETs are in series, and the P MOSFETs are in parallel. Okay, and NAND, a NOR looks like, again, looks like 4 transistors, but here the P MOSFETs are in series, and the N MOSFETs are in parallel. It's like my camera ran out of battery. Well, you guys don't need to see me. I'm not trying to hide on purpose. All right, so Y, okay, so that's what that looks like in NOR. And then an inverter, whoops. Looks like this. Okay, so anyway, the upshot is the simple multiplexer, which is a circuit we use all the time, has these 20 transistors. Okay. Now, let's say the circuit though, let's say we got really lazy. So going back to the circuit of the multiplexer, and we made it from, he said, okay, if let's say N MOSFETs for perfect switches. So let's say they're not, the signal strength is not dependent on whether you're trying to pass a 0 or 1 for the sake of discussion. What you could do is make a really simple multiplexer. So instead of 20 transistors, so it could make a 2 transistor multiplexer. So this is if NMOS was that perfect switch. Okay, so what you would do is you'd put 1 NMOS. Well, sorry, you'd need 4 transistors. Take it back. So what you would do is you would have 1 NMOS, and you would make this S, come on. Okay, why is my pen not working? Sorry guys, having technical difficulties here. Okay, S, okay, and then you'd have another N MOSFETs that would get S bar. And I'm going to say to get S bar from S, you need an inverter. So S bar and S. So this is 2 transistors here. And then these, whoops, I shouldn't have done that. And then I give D0 to this guy, D1 to this guy, short the 2 outputs, and this is my Y. Now, if these N MOSFETs were perfect switches, then this would work, right? When S is high, when S is 1, S bar would be 0. So D1 path would be cut off, and D0 would go straight to Y. And vice versa, if S is equal to is low, sorry, I did this wrong. This should be S bar and S. But you guys get the idea. So with just these two transistors, or sorry, 4 transistors, including the what's in the inverter, I would be replacing 20 transistors worth of stuff. Okay, so it is attractive so sometimes we don't use the whole pull up, pull down network in certain types of circuits. And those are usually like multiplexers, one of them. We'll see how you'd also want this thing in a flip-flop or a latch. So those were sequential circuits. But anyway, I just jumped ahead to tell you why we might want to do this and why would this be important. So so what you do in those cases, because you have, again, going back to the concept of our mux, this is S bar S. Short the two outputs together, get Y, D0, D1. Okay, so we have what we just said, so now we got a problem because it depends if we want to pass D0 to Y, say, right? When S is 0 and select a 0, we want to pass 0 to Y. The problem is if you just use N MOSFETs in this case, if D0 is 0, okay, you get the output goes to 0. Okay, we're good with that. But if D0 is 1, Y doesn't quite get to 1. We said it'll get to 0.8. So kind of like a crummy, we'll get to a crummy 1, and vice versa for D1. So what do? Well, what you can do is this concept of a transmission gate, which is another commonly used concept in CMOS logic, which is you put a PMOS in parallel with each NMOS and give the PMOS the opposite polarity. Okay, so if the NMOS gets S bar, PMOS gets S, and if the NMOS here gets S, PMOS gets S prime. And then what happens is if when S is 0, okay, now let's see what happens. The NMOS is on, and so is the PMOS, right? PMOS likes it when its gate is at 0, it's on, and the NMOS is inverted. So now if D0 is 0, the PMOS doesn't do a good job of passing it, but it's in parallel with an NMOS. So cool. So NMOS does the heavy lifting in that case when the input is at 0. So the output becomes a good quality 0 in that case. Okay. So the NMOS does all the work in the case when you're trying to pass a 0. And in the case when D0 is a 1, the NMOS isn't going to do a very good job passing that, but the PMOS is there in parallel. So the PMOS does the heavy lifting, and you'll end up with a good 1. Okay, so this is called a transmission gate, which is basically a NMOS in parallel with a PMOS, with the gates of the NMOS and PMOS being inverted with respect to each other. And that way you're guaranteed to get a good quality 1 or a 0 from one side of this thing to the other. And primary example of that is a multiplexer. It's like we've got drawn here. Okay, another place for that is like a tri-state buffer. which you use. But by the way, was there any questions so far on the transmission gate and the multiplexer use? So just like we had this approach, go ahead, sorry. Any questions? So just like, the baseline situation is we have N and P pull down, pull up in CMOS logic. So that was a baseline. And then the next step we took was these complex gates, where instead of having individual gates making a complex logic function, we sort of broke it down and could use a complicated gate to do that function. Now, furthermore, if we have something like a multiplexer or some circuits like it, we use these transmission gates to make it a more efficient circuit. So these are sort of the exceptions to the pull down, pull up network, just for efficiency's sake. Okay, so another place where you would use these transmission gates or tri-state buffers. So where do you use a tri-state buffer? A tri-state buffer, the concept is that, let's first talk about the concept. So a tri-state buffer is like a regular buffer has two states. It's either, the output is either 1 when the input is 1, or it's 0, output is 0 when the input is 0. Okay, sounds good. A tri-state has an additional state called the Z state, which is a high impedance state. Okay, so where do we use that? We use that's really popular, or when you use it is when you have a bus architecture. So what that means is, let's say you have a signal, and let's say you have a bunch of elements that are using the same output, and each one of them, let's say I just call it like poor drawing here. Well, maybe it wasn't, I don't know how to do it better, but let's say you had a bus, and there's a bunch of components hanging off of that bus, and then each one of these likes to take over the bus in turn or when it's selected. Okay, the problem is if you either have a 0 or a 1 are the only option for these buffers that are in these circuits. If 0 or 1 the only options, then they're going to end up fighting with each other. When this thing is 0 and let's say the other ones are 1 or whatever, they don't let you, the other buffers won't let you take over the bus. Okay, so what happens if you have this high impedance state for these buffers? So if you had, let's say, this sort of a tri-state buffers here, it could be that you put all these in high impedance state, and basically this inverter is taken over the bus, and it's free to switch from 0 to 1 or whatever it's going to do. And the rest of these guys are in this Z or high impedance state that they can't drive the bus. Okay. Now, why are we calling it high impedance? Well, typically when you have a buffer, whether you're driving a resistive load or a capacitive load, in either case, you want the resistance of this buffer ideally to be low. So the series resistance, R sub S, is you'd like it to be low. So I'm going to call this load or C load, because let's say in this case, you have a resistive divider. So here, V out. So V out is V in RL over R sub S plus R sub L. Okay, so if R sub S is really small, is really low, then V out is V in times all this is a V. Sorry guys, just write more carefully. So V out is V in times RL over R sub S from R sub L. If R sub S is really small, you can get rid of it, and V out is equal to Vn roughly. Okay, so you want your buffer to have low output impedance. Similarly, if you just have a capacitive load like we typically have, you don't get this resistive drop option, but you can drive the output faster because you have the RC time constant of your R sub S and the C load, and you want that to be low. So a typical buffer, you would want a low impedance is good in a buffer. So this high output impedance means that you're not, if this R sub S is very large, then it's almost like an open circuit. It's not going to be quite there, but it's going to be a large resistance. And so what this circuit would look like would be one guy who has an R sub S that's low, sharing the bus with a bunch of R sub S's. R sub S is equal to, I don't know, 1 times, I'm going to make it really large. Say giga ohm or something. And this R sub S is equal to 50 ohm, say. So basically, this guy is essentially going to be able to take over that bus because the other guys won't be able to drive it. Okay, so you have this tri-state buffer that can let your output go into a high impedance state. So the way the equation looks is if enable is 0, okay, that means that Y is going to be in this high impedance state, means the output here has a high resistance and it can't really drive its output. It's just sort of floating is another way to look at it. And if the enable is 1, then the output actually follows the input. Like you will have drive. So again, this is important in buses and stuff. So any questions about that? I know that was kind of a very maybe overly detailed explanation of tri-state buffers. I'm just never sure if you guys have seen these or not. But anyway, we already talked about this tri-state buffer. Let's see what this has to say. So you could just use something like this, right? You could use this guy as a tri-state buffer, meaning that I could put a buffer here and either enable or not enable this. So this will work out like a tri-state buffer when enable is high. If enable is equal to 1, then the output follows the input because this guy's on because this is enable bar, right? If enable is equal to low, both of these guys are off. This guy's off, the NMOS is off, and the PMOS is also off, so the Y is just sort of hanging there. So this is a tri-state buffer. And this is called a non-restoring tri-state buffer though, because you are passing through this pass transistor, and this pass transistor itself has some resistance. So it's a so-called non-restoring tri-state buffer. So what you can actually do is put these enables in series with your PMOS or NMOS and get sort of a slightly better tri-state inverter. It does violate the rule that we don't want something on the pull-up network on at the same as the pull-down network, but it's just this sort of the enable, and you still don't get a short because these two guys are not going to be on at the same time, but it does violate this kind of complement rule about things being on, being on both the pull up and the pull down. Any questions about that?
No questions.
Okay, great. Let's see. So multiplexers we already talked about. So we talked about this. Okay, inverting mux. It's not too interesting. What is this trying to sell? So I mean, I guess we could just sort of make, if you want to make higher levels of multiplexing, we can do that. Again, these are either with, there's two ways of getting higher level of multiplexing. You can either use these tri-state type buffers, or you can put multiplexers in series. Now, one problem with putting multiplexers in series like this is, like we talked about, you're going to go through multiple layers of pass transistors or transmission gates, like from here to here. And so each one of these layers has a resistance. So your sort of signal quality, you still get a full voltage value. You just might have a hard time getting, like the resistance starts going down here, is increasing because each one of them has a resistance. And then if you're driving a capacitance, it could slow outputs down. So I have to be a little bit careful about that. Okay, so next. So now, okay, so what did we talk about? So we talked about combinational circuits so far. Okay, combinational circuits are things like ANDs, NANDs, inverters, multiplexers. And the reason they're called combinational circuits is because the output is a combination of the inputs, combinational circuit. But in a combinational circuit, doesn't really have a concept of time, in the sense that it has no concept of what happened previously. So, for example, imagine if you have a vending machine. Okay, so you want to design a vending machine from CMOS logic, etc. If all you had were combinational circuits, when you drop the coins in the machine, and so you sort of, let's say, you drop the coins in the machine, and then you select a Diet Coke or something. When you select a Diet Coke, you're not in the process of feeding money into the machine. You fed the money into the machine one cycle ago. Okay. So, but the machine can't remember that, right? Because it just has combinational circuits. So you need something like a sequential circuits that remembers that some time ago, whatever, a unit time ago, or the last clock cycle, or 10 clock cycles ago, you did something, like 10 clock cycles ago, or whenever it was, or a millisecond or a second ago, you fed $1 into the machine, and it puts the machine in a state that now it's ready to dispense your Diet Coke when you hit the button. So that's what you need sequential circuits for. That's one use for it, is when you want to put your machine into a particular state or some other state, depending on what an input was at a previous time. So those are called sequential circuits. And so an example of that is a latch. And the idea is that for a latch is if the input is a certain value, it doesn't pass to the output until the clock arrives. Okay, so now you're talking about, now there's a concept of time because there's a concept of clock. Okay, so D could do anything here until the clock arrives. It could be 0, it could be 1, whatever. The output, notice the output is not following D, Q. But as soon as there's a clock, the Q starts following. Here's when the Q starts looking at the input D and starts following D. And as long as the clock is a high state, the Q follows D. So if D goes down, Q goes down with a little bit of delay in between. Okay, so from when the clock is high, the Q follows D. The rest of the time, so around here, Q is ignoring D. Here, Q is ignoring D, and only here is it following D. Okay, and notice that the Q holds its value when the clock goes low. The Q holds its value. Okay, so again, if D is if Q was high at this point, because D was high, then the Q would hold its value. Okay, is there anybody? I'm just to trying to get a background. Is there anybody not familiar with like latches or sequential circuits or flip flops? Everybody's kind of roughly familiar with how they work. I'll take that as like, yes, you guys are familiar with it to some extent. Okay. So you can make a latch using a multiplexer and so notice we had two things we wanted from a latch. We wanted if clock is high, we wanted Q to follow D. If clock is low, we wanted Q to hold previous value of D or hold its value, let's say. Okay, so let's look at this. So you can make it with, you can make this D latch with 4, basically, no, say 6, well, let me not get into that, but you can basically make it with a multiplexer and 2 inverters. Okay, so let's look at the case when clock is high. So when clock is high, say you select this, and this guy just goes to the output. Okay, so Q becomes D, and Q bar is D bar. Okay, so that's when clock is high. So we've got this covered. Okay, and so now let's see what happens when Q or clock is low. So when clock is low, you select this input, the multiplexer. So what you get there is you get this path here. And notice this is this path has a feedback loop. It's basically you've created 2 back-to-back inverters, meaning that let's say Q was let's say previous cycle before clock went to 0. Let's say D was high, so Q was 1 and Q bar was 0. Okay, So what happens is Q bar was 0, we inverted it again. So the output here at this point is a 1, which puts a 1 back here and keeps Q bar's output at 0. So it's a positive feedback loop. A positive feedback loop, the circuits are working to keep their previous value, okay? So then let's look at the case when the previous value of D was 0. So Q is equal to 0 and Q bar is equal to 1. So again, this guy inverts Q bar, gives you a 0. So you get a 0 out here because a mux is selecting that. And then keeps, that way you keep the value of Q bar at 1. So it just sort of locks itself up as soon as you put it in this positive feedback mode, okay? And the way you basically design it is this is your multiplexer, okay? So now, sorry, so this is, if you design this, so just let's stay glued to this part of the picture. So if I implemented this just the way I said, okay, I would do it like this. Would have one guy, the other guy, and then D would go to here. This would be clock. This would be clock bar, and this would be clock. And then, so that's sort of what my multiplexer would look like. Yep, and then this would be, sorry, this would be Q bar and that would be Q. Okay, but the actual implementation, it's actually kind of better to implement it like using this, okay, method. Why is that? Because, you know, in this case, well, let's see, why is that? I'm trying to think. You have, man, I'm blanking about why we're doing this. For a very good reason. Let's think. Here we're isolating this guy from this guy, but we were doing that anyway. Right? No, it's exactly the same circuit. Sorry, guys. It's exactly the same circuit. Sorry, I just draw it differently. I just had to confuse myself. Anyway, so that's sort of what it looks like. You end up with this D latch. Okay. So I think we talked about this, what this D latch works already. Okay. So another sequential circuit that's probably used a lot more, not probably, definitely used a lot more than the latch, is a flip-flop. So a flip-flop is also kind of works like a latch, but it works on the rising edge of the clock, or it works on an edge of a clock. It doesn't have to be the rising edge. It's either rising or falling edge of a clock. So what does that mean? Let's say it works on the rising edge of the clock. So when clock, it's only when clock rises does Q change its value to whatever D is. Okay, only on this edge. Okay, the rest of the time, Q ignores D. So notice here, Q was stated its previous value, D was changing until you saw a rising edge of the clock, and then Q changed to whatever the D value is. Here, when D is switching, the output doesn't do anything because there's no rising edge of the clock. It's only when we get to this rising edge and now D is at 0 and then Q goes down. Okay, so basically it's another sequential circuit, but it's edge triggered sort of rather than level sensitive, like a latches. Okay, and basically we can build that by putting two latches in series with each other and inverting the clock phases in between the latches. So the way it works is the output gets to this point in the middle when clock is, in this case, when clock is low, the D goes to here, but it doesn't propagate all the way to Q until clock changes state from low to high. So when clock goes from low to high, this value of this D goes to the output. But also, when clock goes high, you've cut out the path from the D to this point. So basically what you're doing is you're putting the signal from the D out to the output of this latch, but you're not letting it to go to the output until the clock changes state. But at that point, you're also not allowing this value to change. Okay, so that's a flip-flop. Okay, again, it's edge trigger. Okay, let's talk about a few things that, so again, I don't know how familiar you guys are with setup and hold times and race conditions and things like that, but when, if you have two flip-flops, it's not guaranteed that the clocks, so it's not guaranteed that this clock gets, is the same exactly as this clock. So it might have a delay between those clocks. Let's say one of these flip-flops is on one side of the chip and the other flip-flop is, like a centimeter away. So this clock might have a pretty large skew. So it's a time skew, because there's like R's and C's and stuff in between. There might be buffers. We'll talk about all this stuff in detail, but the upshot is, and let's say this output goes directly to that input. This output can change before the clock edge arrives. So if you have a big delay in clock 2 compared to clock 1, you could have a case where the output just sort of races from D straight to Q2 because at first it goes to Q1 and it has time to settle at the output of the Q1 because of this rising edge. Okay, and then that's exactly when clock 2 arrives, and then you can go from Q1 to Q2. Okay, so that's called a race condition because, ideally, not ideally, but what you'd like it to happen is this is sort of like a pipeline operation. You'd like this to go here in one clock cycle, and the next clock cycle you'd like to go to the output. But effectively, because these clock cycles are delayed with respect to each other, then it can go all the way through and effectively in one clock cycle. So that's called a race condition. We're going to look through that in detail, but it's something you need to worry about in flip-flops. And again, we're going to go into details in all these circuits. So this is supposed to be giving you guys a background or an overview of the different aspects of CMOS technology, okay? So one thing you can do is this business of non-overlapping clocks. So you could have a clock, two clocks that are out of phase with each other to prevent this race condition. And it's a way to get like a safe operation of a flip-flop in CMOS technology, but it's really only used in sort of research environments because it's really in a big chip. It's like it's hard to create and inefficient to create um, a non-overlapping clocks. You don't want to be routing multiple clocks when you could route only one. And then you can't go very fast with using non-overlapping clocks because you tend to lose the non-overlapping aspect of them as they see different R's and C's and buffer delays, etc. And we'll talk about that in detail. Okay, any questions so far? So we covered static CMOS, we covered, which had pull downs and pull ups of N MOSFET and P MOSFETs. We covered using transmission gates that we normally don't like pass transistors, but transmission gates work okay. And then we looked at how you can use those in multiplexers and some other specialty circuits like a tri-state buffer. And then we looked at sequential circuits in CMOS like latches and flip-flops. Okay, so that brings us here. This is sort of covering all the different flavor type of circuits of logic in CMOS. In addition to these, we have other things like memories, which are like static RAM cells or dynamic RAM cells. We have like some other kind of circuits, but this is sort of 99% of your circuits or combinational circuits made from static CMOS logic and transmission gates, and then sequential circuits made from latches and flip-flops. Okay, and then we'll look at some of that extra 1% later. Okay, so now let's talk about, we've got from a circuit perspective what these CMOS gates and sequential circuits look like. So from a schematic point of view, but like we talked about in like 2 lectures ago, was that you would have to actually build a sort of a drawing of these circuits, and that's called a layout that you can give to the factory to make these gates. Okay, so we're talking about a little bit about if you're going to make these gates, what are some good design practices to use? Okay, and so let's say we want to make an inverter. So just as a reminder of so inverter, we've got a P MOSFET on top, and we have an N MOSFET on the bottom. The gates are connected together. The output is connected together. The source of the N MOSFET is going to ground. The source of the P MOSFET is going to VDD, or the power supply. And again, the drains are connected together and the gates are connected together. Okay, so it looks, if you lay that out, this is one possible implementation. You could put, so this ends up being this is the source of the NMOS that goes to the ground. This is the drain of the NMOS that gets connected to the drain of the PMOS using this metal layer. And then here's the source of the PMOS. Notice that the PMOS, we know it's a PMOS because it's sitting in this well, which is an N well. It's not indicated here, but you start being able to read these things. Okay, so that's one possible implementation. But I guess you could have put the NMOS like this with the gate hooked up like this. So this would be the poly gate. This would be this. And the source and drain would be like that, as opposed to it lying horizontally. Okay, that could have been one option. And then the other option could have been you could put the output over here and the input over here. Okay, so you could have a bunch of different options. And this is just showing the same thing, but with the taps for the substrates. Okay, but because you want to make your life easy, because your layout isn't just going to be one gate. So this is one inverter, but you're going to have one inverter going to a NAND gate, going to, I don't know, like a NOR gate that its inputs are coming. So you're going to have a bunch of circuits, right? Constant bunch of circuits. So there's a bunch of good layout practices that make things efficient, okay? So what you'd ideally like to do is to create a library of these cells so you can use them over and over again. So that's like a very important idea, is the cell library. Meaning that, let's say, what you do is, and in fact, you can usually get this from the foundry, or you make it yourself. Let's say you'd have in your library, you have, you know, 3 flavors of inverters with different signal strengths, and we'll see what that means. You might have like a NAND gate, NOR gate, multiplexer, and so on. So you only do this layout once for each one of these. And then as you build different kinds of circuits, you just go pull these parts from your library, or your computer-aided design tool goes and pulls these things from the library and uses them. So to automate that, you'd like to use some techniques to make all these things fit together nicely when later on you go and sort of put them together. Okay, so these are these kind of rules, and this is called the standard cell approach. One thing is you would ideally, you would like to have all of them, all these different cells to have the same height, okay? Meaning this height, you'd like all of them to be at the same height. They could have different widths, but you'd like all of them to have the same height. Because let's say this inverter that we have here, let's say this guy wants to drive a bigger inverter for whatever reason, right? So that way, if we draw it like this and we keep the same height, we can have that guy have, you know, a fatter PMOS and a heftier NMOS. But if they have the same height, this ground can connect both of them together, and VDD can connect both of their VDDs together. Okay, this output from this guy, because it's on the right side, can go to the input because that's on the left side. So basically I can put another buffer butted up against this guy, and just the power supplies will connect up with each other and line up, so I don't have to push those up and down, do a lot of extra work. Notice that always the N MOSFETs are at the bottom, and the P MOSFETs at the top. Again, that will allow the wells to short to each other if you're just connecting them up together. And also that the power supplies, the VDDs are on top, grounds are on the bottom. Okay, all the substrate contacts sort of work together. So basically, you have a situation where you can butt these things up next to each other and they're all line up. Okay. This is talking about the specifics. I don't know if it's just talking about the specifics of the rules about what you end up with as, a typical height, because you have to take into consideration that, you'll have a ground and you'll have an output and you'll have a supply, and you need to run some wires and so on. So you end up with a certain minimum size gate height. And it's claiming that that minimum gate height is going to be 40 lambda for all your gates, and they'll have different widths in this sort of a standard cell approach. Okay, any questions, guys? Okay. And so let's see. So now it brings us to our next. I do it file app. And then didn't like that. Oh, it's working on it. I just wanted to, I don't think we'll have time to get into the next slide deck. I just wanted to give you guys a heads up about what we're going to be covering. Of course, it's taking forever. Well, okay. So what we're going to, so this lecture that we just gave, or we just had, what was in the Royal when we just saw together, was the end of our sort of introduction. So what we talked about was the history of semiconductors, the semiconductor business, chip design business. Then we talked about the economics of putting chips together. We talked about the factory, ways of making those chips by using different layers. We talked about how you might make mask layers to communicate with the foundry. We just talked about how you would design these logic gates in CMOS. And then we talked about some of the good qualities of a logic family. We talked about the transfer function. We talked about speed. We talked about noise margins and stuff like that. And so that is all sort of introduction stuff. And so going forward, in the next chapter, we're going to start diving into the details. Okay, so then we're going to start basically by doing a review of the transistors, of the MOS transistor. And so we'll walk through an NMOS, PMOS, how they work. And so instead of like a switch, we're going to see them as sort of the next level of complexity of voltages and currents. And then once we're done with that, we're going to put them together again and see what the actual gates looks like. Instead of being just switches, we talked about NMOS has a hard time getting a 1 through it. We'll look at what that means. Same with the PMOS. We talked about transmission gates, etc. So we'll see what that actually looks like in terms of voltages and currents and the why. Okay, guys, any questions?
No questions.
Okay, if not, so we'll stop here. Have a great weekend, and on Tuesday we're gonna jump into the MOS transistor. Thanks, guys.
Have a good one.
You too. Take care.
Thank
Thank
you.
you, Professor.
Thanks.
Thank you, Professor.
Thanks. Bye.